So in this talk, I'm going to take a real world example to illustrate the idea that the meaning of a partial derivative depends not just on the variable with respect to which you're differentiating, but also on what other variables you're keeping constant. So in economics and other disciplines, the social sciences, there's a term that's often used, and that's keeping other things constant. What's the technical term for, like, in economics?
Ceteris paribus.
Ceteris paribus. And what this insight from partial derivatives is telling us is that ceteris paribus, which just says fixing everything else you're doing an analysis of one variable and the relationship or relation between the function of many variables. You fix all except one and calculate partials. That's not really well defined unless you specify exactly what those other things are that you're holding constant. So this is sort of, whenever you see somebody say ceteris paribus, you should ask, like, what are those ceteris that are being kept paribus? Okay, so I'll take a simple example here. It's a somewhat artificial example. I don't want to take anything controversial, so I'll take something which you probably don't have much opinions about, which is military spending. I'm going to assume a model where a country's military spending depends on only two variables, the per capita GDP and the population. Okay, so let's say you have a function, I'll call it capital F. I'll use MS for the military spending. Let's say MS is a function of the GDP per capita, which I will denote, and the population. That means that if two countries have the same population and the same per capita GDP, they'll have the same military spending in this simple model. Okay. Now suppose I ask you, ceteris paribus, what happens to military spending when I change per capita GDP? So what would you say? Well, how would you try to measure that, quantify that? You would say, consider the partial derivative of military spending with respect to per capita GDP. What's that? That's capital F sub per capita GDP of But actually, I wasn't precise when I just said ceteris paribus, how does military spending change with respect to per capita GDP? What should you ask me when I say ceteris paribus something something?
What is ceteris that you are keeping paribus?
Or whatever. I don't know if I'm getting the Latin right there, but what is it that you're keeping constant? Now, in this case, what are we keeping constant?
Population.
So the what we are saying is, if holding population constant, you change the per capita GDP, there's every individual, or maybe not every individual, but on average individual GDP goes up, then how does military spending change? Or if you're doing the left-hand derivative, then you say average per capita GDP goes down, how does military spending change? Holding population constant. But somebody else may say, well, population isn't the right thing to hold constant to understand this relationship. What I really should be doing is I should be considering military spending as a function of per capita GDP and total GDP. And now for the function, I cannot use the letter F because the form of the function will be different. So I'll use the letter G. Now, why are these two pieces of information equivalent? Why is it that if I have this function, I can work out this function and vice versa?
Because GDP equals the product of population and per capita GDP.
Yes. So GDP, let's write that down here. Is it okay? Here. That's what per capita means. It's per capita just means GDP divided by population. So this is definitionally true, which means that if you are here, we want to write military spending function of per capita GDP and GDP, then we just look at this original function and replace population by the quotient of these two and then simplify. Alternatively, if we already have this expression and we want to get the expression for this, we just, wherever in this expression where we have GDP, we replace it by the product and simplify. So I can definitely get one expression in terms of the other. So now if I ask you, what is the rate of change of military spending with respect to per capita GDP, ceteris paribus, what should you say?
The partial derivative of f with respect to,
Well, F or G?
oh, g.
G.
With respect
Well,
to,
when I said ceteris paribus, you should first ask, am I doing F or G?
oh,
And then if I say, oh, I'm holding GDP constant, then you'll say, okay. Okay. Conceptually, what is this measuring?
you mean
Like, what is this partial saying?
saying holding GDP constant, and then change per capita GDP, how military spending changes.
Yeah. So if you actually change per capita GDP holding GDP constant, what happens to the population?
The population moves to the different direction with per capita GDP.
Yeah, so population will, if in per capita GDP is increasing, then if per capita, I don't know, but if per capita GDP is increasing, then population will decrease to keep the product constant. And if per capita GDP decreases, then the population will increase to keep the product constant. And so with that kind of change, you're trying to figure out how does military spending change with respect to per capita GDP. So these two things are not actually the same. Okay, these two things are not the same. Okay. So you don't think that's an X. But these two things are not the same. So even though I use the same symbol, they don't actually represent the same quantity. Now, is there a relationship between these? Yes, there is. There's a relationship using the chain rule for partial differentiation. And there's actually a systematic way of figuring out the relation between these, which will also involve the partial with respect to population. And that's actually a more advanced topic, but it'll involve ideas. Well, I'll just say the word here. There's a word called the Jacobian, which actually tells you how to do the transformation. It's a technical idea which you may see later if you do more partial derivatives.